Good evening, and once again welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamoto. And in this video, I want to explain pure mathematics 4, mathematics 4, and we are in chapter 3, where we are discussing example number 5 on page 22. And a curve C has parametric equation given by x is equals to cot t plus 2, y is equals to cosec squared t minus 2, and this t is ranging from being greater than 0 all the way to less than pi. Part A, find the equation of the curve in the form of find the equation of the curve in the form of or rather in the form y is equals to fx, and state the domain of x for which the curve is defined, Okay, let's get to the real thing. Of course, we have this parametric equation, and the moment we have this parametric equation, then if you have x is equals to the cot of x, or rather the cot t plus 2, we have to make the cot t the subject of the formula, and this we know the cot t is x minus 2. And we may call that equation 1 because we would wish to make cot t the subject of the formula, the part that is representing the parametric part, which is this t. We have to make it the subject of the formula so that if there is any substitution or replacement, it will be easier to substitute. From the second equation, y is equals to cosec squared t minus 2, and again we have to make cosec squared t is equals to y plus 2, and this is equation number 2. That is equation 2, so to speak. And let us now discuss. Since our equations are in terms of cot t and cosec squared t, the parametric equations involve cot t and the cosec squared of t, and therefore we can use the identity that captures both of them. And one of the very many identities that we can use here, it is quite special because we have an identity that combines cot t and cosec squared t, which says since, and we know this from pure mathematics 3, in one of the videos we outlined this, 1 plus the cot squared of t is equals to the cosec squared of t. We can substitute this in equations 1 and 2. We can substitute these details in equation 1 and 2. And what do we have? Equation 1 talks about, now, 1 plus cot squared of t. Let's just substitute this and have, but cot t is x minus 2. So 1 plus, what is cot t? X minus 2 squared exactly equals to y plus 2. The only thing we need to do here is simply bracket 1 plus x squared minus 4x plus 4 is equals to y plus 2. And the general equation becomes, we are going to get, if we rearrange clean this one a little bit, y is going to be equals to x squared minus 4x plus 3. Of course, it goes without saying, that is it. Therefore, the range of x, we are supposed to find and state the domain of x for which the curve is defined. The domain of x. Since we know that x is equals to the cot t plus 2, and t is ranging from 0 to pi, both boundaries not inclusive. All those angles between 0 and pi, each one of them has a specific cot, and that cot, then we add 2 to it. You will have so numerous values of x, meaning that if we substitute, or rather we can say the range of x, the range of x being equals to t plus 2 over the domain of t, the domain whereby t is from 0 to pi, is all the real numbers. Because if you substitute t in this one and start with t slightly greater than 0, bring it here, probably 1, 2, 3, 4, all the way to pi, in each and every time adding 2, you will have numerous real numbers. So therefore, x is a member of, and that is like it. So part B, y, we are supposed to sketch the curve. Are we sketching? Y is equals to x squared minus 4x plus 3. If you look at this one, is a quadratic equation, and therefore we start asking ourselves two questions. Which two numbers we add, they give us a negative 4, and the same numbers we multiply, they give us a positive 3. Of course, it goes without saying that x squared minus x minus 3x plus 3 is what we're going to take to be 0. So x minus 1 minus 3, x minus 1. At the end of the day, we're going to have x minus 1, x minus 3. And in this case, these are the critical values. Our critical values are x is equals to 1 or x is equals to 3. And if we are sketching the graph, we must have it this way now. X is equals to 1 and x is equals to 3, critical values. Of course, as x approaches negative infinity, what happens? Let's talk about 0. 0 minus 1 is minus 1, and 0 minus 3 is minus 3. That means minus 1 times minus 3 is positive. So y approaches positive infinity. As x approaches positive infinity, say what? Like 4. 4 minus 1, 4 minus 3. 4 minus 1 is 3, and 4 minus 3 is 1. So 3 times 1 is positive. Again, y approaches positive infinity. So this, as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity. And of course, when x is 0, let's find out. When x is 0, minus 1 times minus 3 is 3. So y-intercept is a 3. So we have our curve that simply looks like that. And fine, yes, that is it. Hence, sketch the curve. We have sketched the curve, and the curve is symmetrical along y is equals to 2, and you just substitute y is equals to 2 here. 2 minus 1 is 1, and 2 minus 3 is minus 2. So 1 times minus 2 is minus 2. So this is 2 minus, this is 2 minus 1, 1, and 2 minus 3 minus 1. So 1 times minus 1 is negative 1. So this particular coordinate is 2, negative 1. It's symmetrical along the line x is equals to 2. Okay.